Good afternoon. Today's lesson is an introduction to materials. Materials are substances that all things are made from. Over 76,000 individually unique materials that are listed in the MatWeb material database. What materials do you see around you in your house or in your classroom? Throughout history, cultures have been defined by their ability to use and select and modify materials. Remember learning about the Stone Age and Iron Age based on what materials they used. Can you think of a time here in the U.S. when material availability played a critical role in defining culture? For example, when the introduction of plastics and how that's changed our society. Is American culture currently being defined by availability and demand for materials? Materials continue to change the world. Advancements in materials technology as well as science create continued advancement possibilities for each sectors, technology advancements, science advancements, as well as materials advancements. What makes material? Materials elements consist of only one type of particle or atom, and elements cannot be broken down. Material composition is a criteria for element classification. We use individual properties to classify elements. We group elements by shared properties. How much of the element you have is irrelevant. It's going to have the same properties whether there's a few atoms or millions of atoms. We classify elements into three categories based on their physical properties, such as boiling point, melting point, density, its color, hardness, and texture. We also classify them based on their chemical properties. Do they react to acid, oxygen, or flammability? The three categories are metals, nonmetals, and metalloids. You've probably learned about this in chemistry. If you haven't, you will once you get to chemistry. Metals are good conductors of heat and electricity. That's why we use them for wires and also for pots. They tend to be hard, shiny. They tend to reflect light. They're malleable, which means you can bend them. You can bend wires. They're ductile, which means you can go ahead and stretch them. You can make them into sheets. They typically have 1 to 3 valence electrons. That means 1 to 3 electrons in the outer. Nonmetals tend to be gases at room temperature, such as these neon lights that you see on the right-hand side. When they're in solid form, such as this glass you see at the bottom left, they tend to be dull, brittle, and powdery. The electrons tend to be tightly attracted to the actual atom, and they tend to be poor conductors of heat and electricity. Metalloids are kind of a mix between, such as silicon that we see in these chips at the bottom left, and arsenic, which is also used in computer chips. They possess both metallic properties and non-metallic properties. Compounds are really what most substances are made of, created when you have two or more elements that are chemically combined. Properties are different than the elements from which they're combined, such as this metal right here is a compound. These materials right here on the right-hand side are compounds as well as liquids. Compounds are element combinations that are not random, but based on specific mass ratios. For example, water is basically a ratio of 1 gram of hydrogen to 8 grams of oxygen. So water has very different properties than the hydrogen by itself or oxygen by itself. Compounds can only be broken down through chemical processes. They can't be broken by physical processes. You can't hammer water and break it apart, but you could use chemicals to separate the hydrogen and oxygen to separate them. Mixtures are non-chemical combinations of two or more substances, such as we've got this cookie that's got chocolate chips embedded in it. The elements in the mixture retain their identity. So all these chocolate chips are very chocolatey throughout the actual chip. Don't have a definite ratio, and they can be physically separated. It would be a challenge, but you could certainly separate out the actual cookie part from the chocolate part. Material classifications are based on their composition as well as their properties that we distinguish them by, such as metallic materials, ceramic, organic, polymeric, or made from polymers, composite materials. Metallic materials to be pure metal elements. They're not commonly found or used. You can use them, let's say, like for copper, but it's not commonly used. Typically, we'll combine the different types of metals. More commonly, metals will be together. Different types of metals will be combined to make an alloy, such as in this wheel that you see on the right here. Alloys are commonly used because of the engineered properties of the compound. It may be better than, let's say, the actual individual metal or the individual element by itself. They also can be thermal and electrical conductors. Their mechanical properties include strength as well as plasticity. Plasticity is basically can you change its shape? Kind of like clay is very plastic because it's very easy to change its shape. Ceramic materials consist of both metal and non-metal elements combined together. They are thermal insulators as well as electrical insulators. Their mechanical properties include high strength at high temperature and brittleness. Their applications could be in clay, which is shaped, dried, and fired. Clay is used in bricks, like in your house, tiles, like you might have in your on your bathroom or kitchen floors, sewer pipes, like you see in this image here, bricks in your chimney flue, china or porcelain that you might have in your kitchen or in your bathroom. Ceramic materials are also sometimes used in refractory conditions, such as if they're designed to provide acceptable mechanical or chemical properties at very high temperatures, such as the space shuttle. The old school space shuttle had silica insulating tiles because the space shuttle would get very, very hot when it's entering the Earth's atmosphere. Ceramic materials have electrical applications. They're used sometimes as resistors, which are these cylinders that you see at the top right. They're designed to create a desired voltage drop and limit the amount of current that goes through the material. Electrical ceramics can be used in thermistors, which are used in the application of heat as it regards current flow, can be used for measurement and control. For example, let's say in your thermometer or thermostat in your house, where you have the thermostat is designed to turn the heat or air conditioning on or off at a particular temperature, that would be a thermistor inside it. They can also be used in rectifiers. Rectifiers allow current to flow in one direction. For example, if you're trying to take in a phone charger takes AC, which is what comes out of the wall, and converts it to DC, which is what your phone needs. So that's what we call a rectifier. So ceramics can be used in rectifiers, such as in phone chargers. They can also be used in heating elements for furnaces. Organic materials either are or once, at one point in time, were living organisms. They're mostly carbon hydrogen. For example, the paper you see at the top right, this food that you see at the bottom right, this twine made from natural materials, plants at the bottom right. Organic materials are genetically alterable. They're also renewable, and they tend to be sustainable. Polymeric materials have distinguishing characteristics. They're mostly organic elements. Plastics are made from plants that were, from a long, long time ago that experienced lots of pressure that created oil. They tend to be low density. Their mechanical properties include flexibility and elasticity. You can make them stretchy like a rubber band. They include both plastics and elastomers. Plastics can include thermoplastics, such as most recyclable plastics. They're formed into shape by applying heat, pressure, and cooling it, and they can be heated and remolded and made into new plastics. Thermoset plastics are not as easily recyclable. Things like this baby bottle here, they tend to be formed into shape by applying heat and pressure and cooling it, so they can't be heated and remolded and made into something and recycled very easily. Elastomers are something that can be natural or synthetic materials. They can be stretchy, like rubber bands made from rubber trees, or like elastic can also be made from latex, which is plastic based, which is a synthetic material. They can be stretched 200% of their length at room temperature, and then very quickly return to their original length. You can take those same similar types of materials, but put them through a vulcanization or chemical process that basically is used to form very strong bonds between those adjacent polymers, and then they'll produce very very tough, strong, hard rubber, such as in car tires. Composite materials are composed of more than one type of material. They tend to be designed to obtain desirable properties of the individual material, such as these fiberglass boats here. Composite materials could include layers of, let's say, wood or materials combined together, such as this plywood you see at the top right. Composites can also be made of particles or particulates, where you have specific or discrete particles of one material surrounded by a matrix of something else, such as this asphalt that you see in roads or your driveway, parking lots. Uh, Composites can also be fiber reinforced, that are fibers that are embedded inside a matrix of other materials, such as fiberglass in the boat that we saw. It could be the composite material that you see in this bicycle on the right, or even Kevlar, which is a material that's used in very lightweight very lightweight bulletproof vests, such as what a police officer might use. Materials can be selected based on their application, their required properties, as well as budget. Their applications can vary from electrical components to building large-scale civil engineering projects, like you see here, cranes building some stuff here. Initial material property considerations are going to typically include what's the product going to do, how's it going to function, what the environmental conditions are going to be, is it going to be exposed to water, air, extreme heat, extreme cold, and also does the material degrade. Refined material selection can be based on a technical analysis and also structural analysis of the materials, and also by examining their properties, mechanical, physical, thermal, electromagnetic, as well as chemical properties. Mechanical properties are, do they deform and fracture in response to strength, in response to mechanical forces, such as strength, hardness, ductility, as well as stiffness. Thermal properties are they affected by heat flux and temperature changes, such as the thermal capacity? Okay, for example, water has a very high heat storage capacity, very high thermal capacity. Can it hold a lot of heat? Thermal conductivity is, can it transport heat? Again, metals are very good at transporting or conducting heat. Thermal expansion is how the material expands or contracts in different temperatures. Sometimes we want materials to expand a lot. Sometimes we want them to expand less, depending on exposure to, let's say, heat or temperatures. Electrical properties are basically, how does it respond to electrical and magnetic fields? Is it an electrical conductor? Is it an insulator, a dielectric, a semiconductor, semi-metals, conductors, and superconductors? Thermoelectric properties are, does the electrical stimuli provoke a thermal response? Or does thermal stimuli provoke an electric response? Again, such as, do you want to put that inside a thermometer or a thermostat that's going to have heat or air conditioning turn on or off? A new type of materials are what we call alternative materials. These are alternative ones that they're developing. Well, they're constantly coming up with new ones. Alternative materials are being designed to solve socioeconomic problems such as sustained economic development, as well as depletion of natural resources. These include things like fullerenes, which are a form of carbon. A carbon fiber, for example, might be used in really high-end bicycles. Liquid crystals, biocompatible materials, or even microelectronics.